Hello everyone, myself Sunanda. I am working as a assistant professor in the Electrical and Electronic Engineering department in St. Martin's Engineering College. So today we are going to discuss about one of the topic in the control system, that is modeling of mechanical system. What this mechanical system consists of? So mechanical systems consist of certain components whose are required altogether forms a system which will require to model, because for any system, if you want to have a stability or if you want to know about the system, we have to know about how the effect of the input over getting our desired output. So we required for a system to be stable is that for a given input we required our desired output. So in between, how these system components are analyzed, right? So here what we are going to see is our mechanical system. Basically, mechanical systems are classified into two types. So one is translation system and another is our rotational system. So let's see what are these types of classifications what we have and what are the parameters what we have in writing the equations. Because any system will be writing or analyzing by using our differential equation. So let's see what are the classification of mechanical system we have. So mechanical systems are classified into two types. So mechanical systems we have are translation system and rotational system. So first we have is translation system. So the name itself says what it means. So translation system is a system where you have a linear displacement. So the motion will be a linear form. So whereas the rotational system, second type we have is rotational system. So rotational system, the name itself gives us a meaning that there will be a rotating motion. So here first of all, let's see what are the inputs we are giving for the mechanical system and what are the outputs we are getting. So translation system or any mechanical system, basically we have our input as force. So input we have is force, which we are representing with f of t if you take with respect to time. Then we have the concerned output. Our output is nothing but what we are having is displacement. So displacement, that is also linear displacement. So let's name it as a x of t. So here x gives our displacement, whereas force is our input. Now coming to the rotational system, in this rotational system the force will be in the rotating form, which we are calling it as a torque. So here the input is torque. So torque generally will go with indicating with capital T of t if we go with the time domain. So then we have our output here. Since it is a rotational force, our output will be not a simple linear displacement, but it will be angular displacement. So angular displacement we will be representing in terms of a angle displacement, that is theta of t. So basically what we have is mechanical systems which are classified into translation systems and rotational system depending on what output we are having. So input for your translation system we are taking is force, that is f of t, with a output displacement represented with x of t. Similarly, in the rotation system we have input a rotational force which we are calling it as a torque, and the output will be angular displacement, that is theta of t. So any mechanical system we are representing with our basic differential equation. For that we required our basic parameters which will define our respective systems, right? So before going to that one, let's see what is the components we have in these both systems. So let's see what are the components we have. So going with the components, here depending on our input and output, both the system have three basic components. Let's see first what is in the translation system. So in the translation system, first component we have is mass body. Element. So what is that mass? How we are representing that mass element? We are representing with a letter capital M. So here mass element is the first element in our translation system. Second element or component we have is damper, or in other terms we can call it as dashpot. So this one we are representing with a quotient called our dashpot quotient or damper quotient, representing with capital B. Now the third component we have is the spring constant. So the spring constant or spring element, we are representing that constant with capital K. So translation system with the input force, output, x of t, that is displacement, and having the components like our elements, mass element, dashpot, spring. So all these three elements together forms our translation system. So here whatever the equations we are writing, we'll write in terms of our force Ft of the each element will also specify. Similarly, let's see first what are the elements we have in the rotational system also, and then we'll move to the each and everything individually. So here in the rotational system also we have almost same three components, but here we have, instead of mass element, we'll face with the another element called moment of inertia. Moment of inertia, which will represent with capital J, the constant. Okay, the two will be similar like our translation system components, that is our dashpot, which we are representing again in the same form, our constant, that is B, and then last one we have our spring constant, which we are representing with K. So here in the rotational system, we are going to have the system with three components, that is moment of inertia and dashpot, and then we have the spring constant, and we have an input of torque with an output of theta. Let's see one by one what these components, how we'll write the equations for these components in both the system. So let's see what is the components we have in the translation system. So we'll go with the translation system. What we have already we have seen, we have three components, that is mass element, then we have our dashpot, and then we have our last one spring constant. So spring constant we have is what last element common with the translation and as well as mechanical system. So we have seen already what all these things we have in the mechanical system, that is translation system, rotational system with all the components. Right, then we have, before going to our translation system, we have a basic parameters what we have to define before we write our equations. So we have first one displacement, that is nothing but change of the position with respect to time, which we are representing with x of t. The second one we have is velocity. Velocity is nothing but change of our displacement, rate of change of displacement with respect to time. So v equal to dx by dt. Whereas acceleration is change in the velocity with respect to time, or you can write in terms of our displacement like d square x by dt square. So these three parameters we are going to use in our force equations of our individual elements. Let's see one by one. So first element we have is ideal mass element. So every element we are going with a ideal element. So here ideal element means a fixed reference we are taking, and we are applying our force, applied force, so f of t. Then we are defining for that element what is the displacement, that is x, okay, with certain reference, and our mass element we are defining with m. So we are representing an ideal mass element like this. Now we applied a force F. So this is applied force. Now there will be definitely an opposing force, that is Fm. So Fm we are representing an opposing force offered by the mass element. Now according to our Newton's force law, what we have is sum of the applied forces. So here only one applied force is there. So F of t is equal to the opposing, some of the opposing forces. Since we are considering here only the ideal mass element, we have one opposing force, that is Fm. So here equal to at a balance condition, or according to our Newton's force law, we are defining F of t equal to nothing but Fm of t. Now how we are writing Fm of t? Our force due to the mass element is equal to or proportional to the acceleration. To remove the proportionality, we are keeping a constant m. So here we are writing acceleration in terms of displacement, that is d square x by dt square. Either we can write in terms of velocity also, that is dv by dt. So altogether our force, which is opposing force of a mass element, is defined as equal to ma, then m equal to m dv by dt or m d square x by dt square. Now let's see the second mass element, second component of the translation system. So second translation system is our ideal dashpot. So here ideal dashpot is nothing but a frictional component. So in the frictional component, we have our B, which we are defining as a dashpot, and then we have our applied force F with a displacement x. So every time it is important to specify our displacement with respect to that component. Okay, so here we have two cases. One is because this is the element may be present between two mass elements. Mass elements are the basic elements which we consider as a nodes. So this element may be present between two or more mass elements. So here we have two cases. One is ideal dashpot with fixed reference, and another one we have is without any fix, or other way we can say is free ends. Okay, so first let's see what is the fixed reference forms we have. So here force equation, again it is an ideal. So F of t will be equal to opposing force of our dashpot, that is we are representing with Fb, which is proportional to our velocity. So remove the proportionality, we are defining a constant b. So here we can write either in terms of velocity, or we can write in terms of our displacement. Coming to the displacement, already we know v equal to dx by dt. So writing that one, everything f of fb will become b dx by dt, because ultimately the output is in terms of displacement. So here fb will be b dx by dt or bv simply. Sometimes we may require in terms of velocity when there will be a conversion of one system to the another system. So better we have the both the definitions. Now coming to the second case, we have ideal dashpot with two free ends. So in these cases, in such cases, first we need to specify what are the displacements we have. So here we are considering in this figure or in this problem, we are considering the displacements as x and x1. Now if we are referring to this side, our node at x with x displacement, we have applied force F. Since it is a ideal element, the force applied force is equal to the what is the opposing force, and only opposing force we have is Fb. So F of t will be equal to Fb of t. Now if we are referring with this node with the displacement of x, then your force is proportional to velocity, or that one is proportional to of the displacement dx by dt. In this we are going to write with x minus x1, because we are referring to the node 1. So similarly, if we want to have the equation on the other side, that is referring to the node x1, then this will become v equal to dx1 minus x2 or x. Here in this case it is x and x1 we have considered. So this will be dx1 minus x when we are referring to node 2. So basically we have ideal dashpot with the fixed reference and with the displacement free on the both side. So this is all about. So ultimately the force equation we have to remember for our dashpot is proportional to the change in the displacement or velocity we can say directly. So here the third one we have is spring constant. So third one we have is ideal spring. So this one ideal spring with the force, opposing force, we are representing with a F of K. We are representing with F of K, and this force we are writing this equation F of T equal to Fk because it is an ideal element. So we are representing that spring constant with K, again with the displacement x, and the force applied is F. So equating the force equation. So here the spring force is directly proportional to the displacement. To remove the proportionality, what we are getting is our constant K. So again in this also we have two things. One is ideal and another one are the fixed reference, and another one we have with the displacement at different displacement or free ends we can say. So in this also, if you consider node 1, here I have taken with the two displacements like x1 and x2. So if you go with the x1, then your f of k will be proportional to x1 minus x2. If you are going with the reference x2, then it will become x2 minus x1. So remove the proportionality, we are replacing it with the constant k. Now these are the basic components in the translation system. Keeping all these three components together forms our mechanical system. So why we are doing all these things means we have to analyze any system with the input-output relationship. So now let's see why we required all these three components or any components mechanical system we are studying. So this is all about to know the relationship between the input and the output, which we'll be defining in terms of a transfer function. So what we are defining transfer function? We are defining transfer function as in the linear time invariant, we are defining it's a ratio between Laplace transform of the output to the Laplace transform of input. So any Laplace transform we are defining in S domain. So here output is y of s and input is our x of s. So here the transfer function is given by y of s by x of s. Now keeping all these three components together, we are going to write transfer function of the main mechanical system. So before going to the writing of your mechanical system components and having differential equation and transfer function, what is the procedure we need to follow? So the procedure consists of certain steps. The first step what we are having is, so we know already the system has to be defined by writing our force balance equation. So in the force balance equation, what we have defined according to the Newton's law, applied sum of the applied forces. Sum of the applied forces is equal to the sum of the opposing forces. So using this principle, we are going to write our force equations. Next we have, second step we have is mass elements. Whatever the mass elements are there, we are considering them as a nodes. So basically we are considering mass elements as a nodes. So we have to take according to the mass element. Next we'll solve the problem. In that we'll see one by one. So how many mass elements are there? That many displacements also we have to note down. So that will become our third step, that assuming our distance. If it is specified in the problem, no need. If it is not specified, we can assume as x1, x2, x3, so on. Then we have to, fourth step we have is free body diagram. So according to the number of mass elements, for each mass element, we will be drawing the free body diagram. So specifying what are the forces have on that body according to the mass element. So then we are writing with their respective force forms in the form of a differential equation. Once we get everything force equations in the differential equations, then we'll convert that one into Laplace transform form. So basically we require certain Laplace formulas, so that we'll use and convert that one into the Laplace form. Thereafter, according to our definition of the transfer function, we will be writing our transfer function, that is ratio of Laplace of our output by Laplace transform of our input. So let's see one by one in a problem. So this is our translation mechanical system what we have, right, with all the three elements together, right. So here from the observation what we have is basically how many mass elements we have? 2 mass elements we have, that is M1 and M2. So we should take M1, M2. So number of the mass elements are nothing but number of the nodes. Now for each mass element we have to specify our displacement. It's already specified in the problem, x1, and another one we have is x. So we have first thing is number of nodes, that is number of mass elements, and their respective displacements. What we have taken is x1 and x. Now let's see what are the forces that have on each mass element. Let's see the first mass element. So first step we have to take is how many nodes are there, then what are the distance specified, then we have to go with the what are the force equations or forces that are there on the mass element. So first let's consider M1. So M1, if you see from the diagram, so every time once we have to remember is the force by itself, that is there will be opposing force by the mass element. So that mass element force also we need to specify. So first one we have to specify is opposing force by our mass element M1, that is Fm1. So here if you see the mass element, we don't have any applied force effect on the M1. So next if you see the next individual forces that can oppose on this element or opposing forces we have on this element are Fb1, which we have referred as Fb1 force, and then we have Fk1. So these are individual forces. Coming to the common elements that are present. So if you take these two elements are common to the M1 and M2. So here this Fb, we are referring now node 1, that is M1. So that's why we have to write accordingly. So here first let's specify what are the Fb and Fk. In the same manner, here also we are writing the forces on the mass element 2. Same way here we have Fb. Here one thing we are observing is here we have applied force F of t. So here we can see the direction of the forces. So direction here F of t is applied force. Whereas other forces, because of the mass element, because of the B2 and because of the common elements Fb and Fk and the ultimate the displacement x. So here we are showing opposing force in one direction, applied force in the another direction. So these are the free body diagrams what we need to write. So let's see in the next step. Next step is for each free body diagram we need to write what are the differential equations. So for the first mass element, whatever the force we have written acting on that body, we have to specify that formulas according to what we have seen with the first derivations. So in that, after having this one, we apply our Newton's force law. So here in this element we have only applied forces which is equal to 0 because opposing forces which is equal to 0. There is no applied force here. So writing all the force equations together and writing their formulas related things, and then next step is to take the Laplace transform. So here basically we use our Laplace transform of basic things, that is x of t equal to x of s, and coming to the Laplace transform of dx by dt we are getting Laplace as s into x of s. So when it was d square x by dt square, we will get x square x of s. Keeping this Laplace transform and rearranging the equation, we will get the last equation x1s in terms of our x of s. So next similarly we will write for M2. M2, here what we observe, we have applied force and also the opposing force. So we are writing f of t equal to the opposing force summation. Then again here also we will write our specified equations and then converting into the Laplace transform method. Then we will get ultimately last two equations related with our M1 and M2 in the form of x1 and x of s. Now substituting our x1 in the second equation, altogether what we are getting rearranging is output by input Laplace transform, what we are getting is nothing but our transfer function. In the same manner, we are going to see what we have in the rotational mechanical system. So in the rotational mechanical system, we have three elements what we have seen. So that elements we have basically are rotational things that are moment of inertia we have, then we have our dashpot again, then we have our spring constant again. So here we have the first one, moment of inertia, which we are defining with the term J, and here the if you see the moment of inertia, because it's an angular displacement, we are specifying in terms of angular motion. We are specifying in terms of angular motion. So here you can see T is the torque, applied torque with an output theta of T. So you can represent even the opposing force Tj, which we'll see later in terms of Tj, we'll write as an opposing force. So coming to the next one we have is our next element, that is dashpot. So dashpot we have is represented with B, and the torque represented with that one we are writing in terms of a T. So here we can see the torque represented with the first one we have is our moment of inertia proportional to d square theta by dt square displacement. Next we have our spring constant, which we are representing in terms of a Tk. So here the torque what we have is equal to the opposing force Tk, which is proportional to theta of T, that is angular displacement. Remove the proportionality, we are getting our K theta of T. So next we have our last component, that is our dashpot, which we are representing with the B, which will be having the displacement of theta T, have the torque proportional to the d theta by dt. So friction constant or dashpot we can say. So in this dashpot we will be facing with the Tb, which is proportional to d theta by dt. So d theta by dt, or we can write in angular velocity thing, that is omega also. So here we have d theta by dt. In this also we have fixed reference, and we have also the other one we have is our fixed and with the free entrance. So if you go with the free entrance, again we'll write in terms of theta 1 minus theta 2. So in these both cases, that is spring constant case and our dashpot case, this is your fixed reference we have. So in this also, if we have the free end, so like this, if you have free end K with the displacement theta 1 and our displacement theta 2. So then we can say whatever the torque is there, that is proportional to the theta 1 minus theta 2 if we are going with the reference of first displacement node. Then in the same way, if you go with the friction also, in the friction also we have another two ends with the displacement theta 1 and another displacement theta 2. So if you go with that one, theta 1 and theta 2, again we'll write our torque is proportional to the theta 1 minus theta 2 if we go with our reference, first reference. So these are the basic elements what we have. So altogether today what we have learned is nothing but what are the classification of the mechanical systems we have and how they have been classified, and then what are the components we have. Okay, then we have seen what are the things we have in the, how we have written our classification things, differential forms. Then we are going with what we have is how to solve the problem we have in all together in the both the translation system. Okay, then we have our equations in terms of angular displacement as well as our theta angular displacement in the rotational system. So we will conclude that one all together in tabular form, that is translation system and rotational system. We have input as a force and as a torque in the rotational system, and we have an angular displacement as a also as an output, and here velocity or simple displacement as a output in the translation system. Then the components we have seen is mass element, damping quotient and spring constant in the translation system, whereas moment of inertia, rotating damping, or simply we can say damping quotient, and we have rotational spring constant in the rotational mechanical system. So keeping all this together, the steps involved what we have seen in solving that gives our relationship between the input and the output. So this is all about our translation and rotational system, basically the classification of total mechanical system, having all this together. So sometime we may require velocity and angular velocity also as output, because in the transforming one form of the system to the another form of the system. So keeping all this together, we can solve any problem related with both the system by using the basic equations and the basic parameters what we have as a displacement, acceleration and velocity. Using this equation, keeping our Newton's second law, that is sum of the applied force equal to sum of the opposing forces, then we can solve by using our Laplace transformation and getting the relationship between the output by input. So this is all together in the thank you.